Our special guest today is Dr. Ellen Stofan, Undersecretary for Science and Research at the Smithsonian Institution. The lecture is made possible by a bequest of the late Major Lester Gardner, a member of the MIT class of 1898. The lectureship is earmarked for annual presentations on aeronautical history. Obviously, it's been broadened since then. Over the years, we've been honored by luminaries in the field, including Igor Sikorsky, Jimmy Doolittle, Von Brill, and Neil Armstrong. Recent speakers were Gwen Shotwell and Charles Bolden. A remarkable individual, Major Gardner played not one, but two critical roles in the advancement of aviation in the early years of the 20th century. First, with the encouragement of Grover Loening and Jerome Hunsaker and Glenn Martin, Major Gardner organized the Gardner Publishing Company, publishing Aviation, Who's Who in American Aeronautics, The Rubber Age, and later Aviation Aeronautical Engineering, which was the predecessor of Aviation Week, which many of us like to read. In addition, Major Gardner was among the founders of the Institute of Aeronautical Sciences, which later became the Institute of Aerospace Sciences, which is one of the progenitors of the American Institute of Aeronautics and Astronautics, AIAA, which is the professional society associated with the field. An air officer in World War I, Major Gardner was a recipient of numerous aeronautical awards, including the Daniel Guggenheim Medal in 1947, given for outstanding achievement in advancing aeronautics, particularly for its conception and organization of the Institute for Aeronautical Sciences. With this as background, let's turn our attention to our speaker today, Dr. Ellen Stofan, Undersecretary for Science and Research at the Smithsonian Institution, in which job she oversees the science museums and science research centers, as well as Smithsonian libraries and archives, Office of International Relations, Smithsonian Scholarly Press, and Scientific Diving Program. With 25 years experience in space administration and planetary science, Dr. Stofan is focused on the Smithsonian's collective scientific initiatives, commitment to research, addressing current issues such as biodiversity, climate change, global health, search for life in our solar system and beyond. As the former chief scientist of NASA, Dr. Stofan served as principal advisor to the administrator on science programs and strategic planning, helping guide the development of long-range plans to send humans to Mars and developing strategies for NASA to support commercial activity in LEO. She holds master's and doctorate degrees in geological sciences from Brown University, bachelor's degrees from the College of William and Mary. She has received the Presidential Early Career Award for Science and Engineers, the NASA Distinguished Service Medal, and the Explorers Club Lowell Thomas Award. Without further ado, allow me to welcome Dr. Ellen Stofan, the 2021 Lester D. Gardner Lecture. Let me turn it over to you.
Thank you so much. And it is such an honor to be here. And of course, all those things at NASA, I did only with the permission of my boss, Dr. Newman here. Let's see. I was just saying, after a year of Zoom, I can actually share my screen. Okay, as I said, thank you. It's such an honor to be here today. And I thought that given the excitement, at least in the planetary science community, certainly, but I think in the broader community also, going on of the last month's landing of the Perseverance lander and the about to be flight of Ingenuity, which Dava has right behind her there. She joined me on Mars. I thought it would be interesting to really talk about this issue of exploring planetary surfaces with robots and humans. For those who are close to the space program, you know that oftentimes there's been a discussion as though robotic exploration of the solar system and human exploration of the solar system are two things that are opposed to each other or in conflict. Why do we need to send humans? There's always been, especially there has been a thread in the planetary science community, sort of, anti-human exploration. And I think we've moved beyond that, but I think it's really interesting to step really far back and look at how we explore planetary surfaces. And I'm going to go through a couple different examples today and how we use different technologies to get the science that we need. And I'm just going to argue that humans are actually just one of those technologies, one of those skill sets that are available to us as we try to answer really big scientific questions. I also have to apologize that I have a hard cutoff right at 3 o'clock because I have to go give another talk. So I want to apologize, but I'm going to try to finish well in advance to answer questions. I thought it would be interesting to start with this slide, which is actually an artist rendition of the exoplanets, some of the exoplanets that were discovered by the Kepler mission. Because today I'm really going to focus on solar system exploration. But one of the things I really want to emphasize is the fact that we've discovered these thousands of exoplanets, obviously with the recent numbers really jumping up with the results from the Transiting Exoplanet Survey satellite, that this is putting our solar system into a much needed and much broader context. So I think this makes this whole question of how we explore planetary surfaces interesting, especially as we move into the era of the James Webb Space Telescope. As we think about larger and larger telescopes, we're going to be starting to use astronomical techniques to do planetary science, which of course we did in the beginning of planetary science, and we'll be circling back around to that again as we start really trying to get at exoplanets. How Earth-like are they? What are the processes that we see taking place? Okay, there we go. Okay, but back to our solar system. So obviously it's been 60 years that we've been exploring our solar system. And during that time, obviously NASA has amazingly been able to visit and in many cases revisit all of the bodies in our own solar system. And given that I'm talking with Alan Stern in my next appointment after this one, I have to mention, of course, including Pluto or Kuiper Belt objects, we have also explored beyond just the major planets of our solar system, and of course, Ceres and comets and asteroids. So a really comprehensive exploration. And I'll be pointing out in a couple different places, this has actually really differed from the exploration plans and approaches that have been used by other countries. And I'll be talking about Venus and Mars today. Obviously, those were the planets that were most studied by the then Soviet Union, now Russia, which chose to, rather than do sort of the expansive reconnaissance of the solar system that the United States did, instead chose to focus on just a few bodies. But I'm also going to argue that as we've gone out and tried to answer scientific questions, it's been a function of both what technologies do we have available to us to go and answer scientific questions, and then of course how much funding is available to actually go ahead and implement those missions. Because obviously as a scientist, if we had all the money in the world, I would be everywhere with some of the most advanced techniques possible, but there's only so much money. Technology is only ever at a certain state. So we balance those things and come up with priorities. And this has now been, as most of you know, put into routine through the National Academy's decadal surveys, which lays out 10-year plan recommendations that they give to NASA, and NASA balances those recommendations against its budget and sets out priorities of what exploration can be accomplished. And as we bring in human exploration, that brings in way other motivations for why we explore. Many of us are good friends with John Grunsfeld, and he put it, I think, better than most people have. He would say we would explore for fear, greed, and knowledge. And the knowledge part is the part I'm going to focus on today. The fear part, he said, was the geopolitical. You know, we're trying to show superiority, as we did in Apollo in the Cold War, to say we have technological superiority. So that's sort of the fear. Greed is obviously the era that we're moving into right now. Are there actually commercial reasons that drive exploration forward? I think many of us feel it's a little early for that, but still, that is a motivator for why we might move into the solar system. And then there's the whole inspiration piece. But today I'm really going to focus on what drives us forward in a scientific sense? And how do those questions become more complex as we move and we learn, which then modifies the questions? And then again, we have to have technology and funding catch up to allow us to actually implement those plans. Let's see. I also want to point out that one of the things we've certainly learned as we've gained more and more knowledge, and as we've been able, as I said in the first slide showing the Kepler exoplanets, that we always have to be really cautious as we frame questions and move outward, because we not only live in a single solar system that we now know differs greatly from many, many of the solar systems we've been able to observe, but we're also exploring our solar system at a point in time. And I really have loved this slide that Don Brownlee put together, because all of these are the Earth. You have the early Earth with a magma ocean. You have the blue Earth dominated by cyanobacteria. You have ice-covered snowball Earth. So you really have to think, we're not only investigating our solar system as a unique place in the universe, we're actually also getting it at a certain point in time. And so as we frame scientific questions, we have to be really thoughtful about the fact that the time in which we are exploring it is not representative of the entire history of that solar system. And that obviously becomes really critical as we go to places like Venus and Mars that we know have gone, like the Earth, through pretty radical changes throughout their history. And so when we're trying to answer scientific questions, a lot of the times we're trying to grab an understanding of something that happened billions of years before, and therefore those questions are quite hard to answer. This is another reason why I'm so excited. You know, most people are looking for that blue planet Earth 2.0. I want to find that really cool magma ocean planet, because, you know, my whole career, people are like, oh yeah, the magma ocean planet. And then we do this and you're like, can we go back to that magma ocean planet? Really cool. And the thought that as we develop more and more powerful telescopes, we're going to actually be able to study examples of these around our galaxy, I think in other solar systems, I think is incredibly exciting. I thought it would be interesting, and obviously this is something we all know quite well, as we think about this question of when do we use robots, how do we change how we explore a planet historically, how do we decide when to do humans, to go through how we normally and how historically we have explored the solar system. As all of you well know, we started with flyby missions, whether it's a Pioneer, a Mariner, a Voyager. Those are the easiest technologically. That's certainly why we started out with them. To get into orbit around a body is hard. It was a technology we didn't have, so we started with flybys. Or we were trying to do something like the reconnaissance of the outer solar system, the Grand Tour mission, where we know, because of a unique lineup of the planets with Voyager, that we could grab a whole bunch of planetary systems out in the outer solar system with one mission, two spacecraft. So we choose a flyby mission partially because it was a technology reason, but then partially because it's reconnaissance, it's easy to do, it might suit a specific situation. But then pretty quickly we want to get into orbit. Why do we want to get into orbit? Obviously, sustained look at a planetary surface, much better knowledge of the gravity field so that we can understand the interior of a planet, and obviously looking at change over a planet with time. We get that global view, the global data sets that then actually help us figure out if we want to land on the surface, where are we going to go? Because we only can land in one place normally, and we want to make sure if we're spending all this money that we're landing in the right place. So using an orbiter, we gather huge data sets to try to understand where best to land on a planetary surface. First steps are always a robotic lander, usually without mobility, because they're easier to do. You have a specific set of scientific questions, usually a combination of measurements of an atmosphere, if there is one, a surface, trying to understand the basic chemistry is normally how we stand out, all the way to more simpler static landers like an InSight lander on Mars that's trying to answer a really specific question for which you need a static lander. You have a seismometer, you want to sit on the surface, you don't want to move, so you go back to that static lander. But as your questions become more complex, as you understand the geology of a surface, being in one place is not good enough. You need mobility. And then your choice of mobility obviously depends on your destination, whether it's ground mobility or aerial mobility. And that is also driven by the geology. Because if you go to a place, and I'll come back to this in a minute as we go to Venus, if your geologic units are tens to hundreds of kilometers across, a rover is really difficult because you're going to have to go really far distances before you actually get to answer the questions you're trying to answer. So in a case like that, you really want aerial mobility where you can get from point A to point B and they're far apart much more rapidly. Sample return is usually obviously the next, if it's technologically feasible, because as you well know, we can't repeat ground laboratories on a planet. We can do really well, but the best laboratories are still located here on this planet. And then a human lander, and whether your human is the vehicle for sample return, as it was with Apollo, or whether humans are doing a function beyond that is something we can discuss. And obviously the moon is going to be the typical sequence of how this happened. It started with flybys, both Pioneer and Luna missions, impactors in the case of the moon, because that was an easy thing to do and get you some good data. Luna, the Rangers, the Surveyor program. The Russians called all their missions Luna. So pretty much you say Luna, you're talking about one of these missions. And then obviously surface mobility, robotic in the case of the Luna missions with the Lunicod, and then sample return with one of the later Luna missions. And obviously the US went to surface mobility and sample return with humans during the Apollo mission. And just to iterate again, even though science was not driving the Apollo program by any stretch of the imagination, it was definitely geopolitical conflict, as we all know. Nevertheless, you still had to follow that similar sequence of exploration because you needed the knowledge in order to be able to conduct safe human operations. So you were not going to be able to land on the surface and move around unless you had had flyby missions, orbiters, landers, this sequence, because you needed to gain the knowledge to understand that it was actually safe to conduct human operations. So those surveyor missions were really critical in understanding the surface density, understanding safe landing sites for Apollo. And so that same sequence of exploration, and actually in this case, there was amazing science that came out of it. It wasn't driven by the science, but you needed the knowledge to actually help move the technology forward to get to where we need to go. And that sequence, especially, I think Apollo also really illustrates that it's technology readiness driven, right? We also started with simple missions. The missions got more complex. We learned to land on a planetary surface. We learned to take back off of a planetary surface. And we couldn't do those things until we had developed the technologies in order to be able to do them. You needed the driver, the science driver, but then you also needed the technological capability to actually go ahead and implement the mission that you were trying to do. So today, I'm just going to visit the similar sequence with some of my favorite places in the solar system. You know, I can never resist talking about Titan down there in the lower right. I'll visit Earth very briefly at the end. I'll start out with Venus there in the upper left. And come around to Mars, which obviously has the most complexity and I think some of the most interesting stories. Now, Venus is particularly interesting, I think, long a target of exploration by the Soviet Union, and that's Venera 14 down there, a surface image from Venera 14 at the bottom of the slide. And as you well know, Venus is a particularly fascinating target in the solar system, and now especially even more so in the context of exoplanets, because here you have this planet that's about the same size as Earth. It's made of, we think, because of similar density, it's made of probably largely the same materials as the Earth. It should only be 10 to 20 degrees centigrade hotter than the Earth because of its proximity to the sun. And yet it's gone through this very different evolution, losing an ocean's worth of water, probably about 3.5 to maybe 4 billion years ago, dominated by volcanic activity as a typical Venusian surface that you see at the top center. These are Magellan data that you see at the top, Magellan radar data, and Magellan topographic and radar data on the globe at the left. So again, an Earth-sized planet, but a very, very different evolutionary path, lack of a magnetic field, just an absolutely fascinating planet. We started, in this case, exploring Venus in a similar sequence. First, we had flyby missions, then we had orbiters. In the case of the US, Pioneer Venus, and then the Magellan mission. And in the case of the Russians, a large number of missions, including a large number of surface landers, as well as the Venera 1516 radar orbiter. And then they also had a balloon mission, so adding that mobility piece with the Vega balloons down to the surface. The US has long investigated going back to Venus with several different kinds of missions, one of which is a static lander for that seismology investigation. Very hard to do because you need to keep a seismometer alive for at least probably 3 to 6 months. You really want it to last for a couple of years so that you can catch not just one quake, but a large number of quakes, and a large enough one that it actually sets up resonances in the entire planet so that you can get a deep interior structure of the planet. Part of the mystery of understanding why Venus went down this very different evolutionary path than Earth did is really to get a detailed interior map. But as we all know, it is 500 degrees centigrade on the surface of Venus. So it is very hard to operate surface landers. As most of you probably know, the Venera landers actually burned up from the inside out because they were so well insulated from the Venusian atmosphere that the electronics inside could not vent. So they actually overheated from the inside, only lasting a few hours on the surface. But we have these hugely significant questions for Venus, like are these rough, bright areas you see in the center of Venus. Those are called tessera. They're continent-like regions. And if they have granitic rock, that would tell you that Venus indeed held a lot of water and held water in its interior early in its history. So the composition of these regions is really critical. So we have to think about what would our ideal next mission to Venus be? There have been a couple orbiters, both from Japan and from Europe, that have gone to Venus, mostly studying the Venusian atmosphere, which has a whole series. I'm a surface geologist, you can tell, oh yeah, the atmosphere. So we've had 2 missions that have really focused on the atmosphere since Magellan, which Magellan ended in '94. So really long time ago. I'm obviously a little bitter about this. And we have not been back to the surface of Venus to address any of these huge questions that Magellan unveiled about why Venus went down this different evolutionary path. In this current discovery round, there are actually 2 missions being proposed, one of which is a surface probe lander that would last for a couple hours, get surface chemistry and atmospheric chemistry. And the other one is an orbiter mission that would get near infrared. You can see through some of the windows in the atmosphere and get some of the surface chemistry, for example, would be capable of detecting erupting volcanoes. And would also get much higher resolution topography, which would help us answer some of these questions. Full disclosure, I'm a collaborator on that mission called Veritas. So there are missions to get back, and we've long looked at mobility for Venus, mostly in balloons, because with a balloon, you could go up to higher levels in the atmosphere where it's cooler, cool your electronics down, use the super rotation to move, and then lower back down to the surface where it's hot, do some surface chemistry, pop back up higher where it's cooler again. Unfortunately, those are fairly complex missions that would require technology development, might require high temperature electronics, and therefore the science is there. We know what questions, we know what we want to do, but the funding and the technology are both lagging behind. So Venus is a really frustrating place, but because of these high temperatures, really expansive exploration of the surface, which is what we see at Mars, is needed at Venus, but the technology is holding us back in a way that doesn't allow us to do it affordably. Now I'm going to go, I clearly like extreme places because I'm going from Venus, which is very hot, to Titan, which is about 90 degrees Kelvin on the surface. And Titan, again, follows one of these typical progressions, first really studied by the Voyager spacecraft in flyby mode of the Saturnian system, one of the largest moons in the solar system. And as you can see from the Cassini image, obviously the next following a flyby, we had the orbiter mission to the Saturnian system of Cassini. Titan is the only body in the solar system with a substantial atmosphere, mostly nitrogen like ours. And Jonathan Lunine and Sushila Treya put together a great paper talking about the fact that methane has this whole cycle where it's being released from the subsurface, goes up into the atmosphere, is photochemically split apart. But you also have this whole cycle where it actually rains methane and ethane on Titan. There's a whole hydrologic cycle with hydrology being replaced by hydrocarbons. So a really fascinating place. And the only other place in the solar system where we actually have open bodies of liquid, in this case, seas and rivers of liquid methane and ethane exchanging gas with the atmosphere, and potentially places to go to understand the limits of life in our solar system. So really interesting place. So even though Cassini was actually an interesting mission because it combined being an orbiter with actually having a surface probe so that you got down to the surface with the Huygens mission. But clearly with the discovery of these bodies of open liquid on Titan, the seas of Titan, which are predominantly located at the northern pole, quickly became an object of study for potential future exploration. So I spent about 5 years working on a proposal for NASA called the Titan Mare Explorer. It's an artist's conception you see at the right. And on the left is a map of Ligeia Mare, which is one of the larger seas on Titan, where you could fit, as you see the dashed line in kind of the center of the sea. That's the landing ellipse, aeroellipse. So you can actually fit landing a probe right directly into the sea, which would then float on the surface. And those are just Monte Carlo simulations of some of the paths that the lander would take, the floating probe, based on wind models for Titan, those windy green lines. And the little rose diagrams are just the elevation of the surface to say how far would you be able to see to the horizon. So this mission is a particularly interesting example of technology readiness, allowing us or not allowing us to go do a more in-depth exploration of a planetary surface. The question was pretty clear, right? Only open bodies of liquid in the solar system, so high priority target, not to mention exploration of the limits of life in our solar system. Does life require water to evolve, or does it just require a liquid? Could liquid methane and ethane serve that role? So very interesting astrobiology target, along with this uniqueness of a hydrologic-like cycle. But the problem is you have to live for a very long time in order to explore this in a very cold environment. So at the time, NASA came forward with a program for what they call government furnished equipment, which was a technology test of an advanced Stirling radioisotope cooler, which used plutonium to create a hot side and a cool cycle to drive a Stirling engine to provide the power. This is perfect for Titan because the waste heat from the ASRG would actually keep the temperature inside the probe at sort of close to Earth ambient temperatures, so you wouldn't have to do any exotic sealing of the capsule. It would just stay nice and kind of toasty inside, allowing us to use conventional electronics and survive on the surface of Titan. The problem is the advanced Stirling radioisotope generators were not at a high enough state of technological readiness to actually be put on a spacecraft mission and sent across the solar system. So in the end, NASA actually abandoned the program for a while of even working on the ASRGs because they were having such trouble getting the technology readiness level up much beyond a TRL-4. And so in this case, it was a really frustrating example. The science is there, the funding was almost there, but the technology actually wasn't ready. You can do this mission on solar, but it's obviously in batteries, but it's obviously very hard. And conventional RTGs make it less optimal. So you really needed a technology solution to help you out with this, and it didn't happen. So that's really sad, but luckily for me, we're still going back to Titan, and for everyone, not just me, luckily for everyone. So you work with what you can, right? There's still lots of compelling science questions for Titan. And so this is Zibby Turtle's Dragonfly mission, which was selected a few years ago. It's an octocopter that will land on Titan. I think right now the date is 33. And explore the equatorial zone where we get intermittent rain. So there are surfaces that get wet and get dry, and there are areas that we think are dried out, areas where there had previously been standing liquids. So again, not probably, in my opinion, quite as good of a target as those seas at the North Pole, but really still able to address some of these outstanding astrobiological questions for Titan, and using mobility in a different way. You know, in the lakes, we were actually using just the wind moving the probe around on the lake surface. But in this case, we could actually use aerial mobility because the Titan atmosphere is so dense, and cover actually pretty far distances and explore a lot of different geologic terrains, from the dunes that you see here in this artist conception all the way to an impact crater that's a little further on its journey. I want to spend the last part, obviously, talking about this place, Mars, that you see behind me and on the screen. And Mars is obviously, you know, as we look at the path of exploration, I find the Mars story to be a particularly fascinating one, because again, you have this very similar progression, right? We went from orbital missions, we refined the science questions, we landed on the surface, we then developed mobility, and right now we're looking at moving into an era of sample return and human exploration. So following very much this kind of cookbook that we laid out with the moon, we've been doing the same thing with Mars, but laid out over a much, much longer time period. And the length of that time period, I'm going to argue, has to do with not just funding and technology, but also has to actually do with the science and how we progress the science forward. So most of you know, obviously, Mars is long a target of fascination because of these dried up riverbeds that you can see that are pointed out, seen in the Mariner data, early flyby missions, but then of course, well mapped by the Viking mission with its 2 orbiters and 2 landers on the surface. And because we got this amazing Viking data set of Mars, we've been able to, with subsequent orbiters, but also subsequent landers, get down to the surface and then use mobility to try to answer more and more sophisticated questions. But with the Viking lander, which is over on the far right, we also stumbled in a way that I think is particularly interesting, because obviously, as most of you know, one of the prime questions that Viking was trying to answer was the question we're still trying to answer is, did life evolve on Mars? And I think a lot of you know the story that my dad worked for NASA. I was at the Viking launches. I was 14 years old to date myself. And Carl Sagan and Jerry Stofan were there, and they were giving talks about why we were exploring Mars and looking for life. And I said, wow, that's really cool. I'm going to be a planetary geologist and do that too. And that's what I've done. And here we still are talking about, was there life on Mars? How are we going to try to figure this out? But obviously, as you well know, the Viking lander experiment used the science that we had at the time and our understanding of life to design an experiment to search for life that was just fundamentally flawed based on Mars and what we now know about Mars. We were never going to get a positive result from the Viking lander experiment. Putting water and nutrient-rich, mixing that with the soil at the top of Mars' surface is not going to do anything for you because of the fact that the top surface of Mars is so heavily radiated, full of things like perchlorates. But we didn't have enough information to design that experiment in the way. So it wasn't that those people were doing anything wrong. They designed the experiment to answer the science question with the information they had at the time. But of course, there was a feeling that when they got a negative result to the life experiment on Viking, that there was a lack of interest from NASA and the scientific community, not really from the scientists, but certainly from the broader public. Oh, there's no life on Mars. It's just another dead planet. Why go back? And as time has gone on, that did have partially cause a pause, along with funding issues of exploring Mars. But then as we got more sophisticated, realized and understood Mars better, we designed more and more complex missions to Mars that really followed this premise of trying to understand. The first thing you have to do is step back and try to understand the habitability. And obviously one of the things that that Curiosity has done for us, and this is obviously a shot of Gale Crater from the Curiosity lander, those beautiful, beautiful layers of rock that we know many of them were laid down in water, this issue that water did persist for very long periods of time on Mars, and that we know that habitable environments existed. We also have gotten much more sophisticated about what would it take to actually find life on Mars. And this is from a NASA astrobiology website called The Ladder of Life that I particularly like, because it really gets to this issue of how do you design a scientific experiment to actually try to answer the question you're trying to answer. And you think that's trivial. Any of us who are scientists or engineers know that's not trivial. It is really hard to make sure you're designing your instrument to really get at the answer when you might not actually know what the answer looks like. And obviously there's now over the last, well, it's not obvious, over the last 5 to 10 years, increasingly interesting study by astrobiologists around the concept of life as we don't know it. Because this ladder of life, which is basically how we go about searching for life in our solar system and then beyond, is really based on Earth life. So we look for biomolecule components, we look for functional molecules like DNA or RNA, we're looking for metabolism, and then ultimately Darwinian evolution when we search or design an experiment to search for life. The scientific community is having increasingly interesting conversations about how do you search for life as we don't know it. And obviously some of these things still hold. So as we go into a new site on Mars with Perseverance, and this is Jezero Crater, where the Perseverance lander is now sitting, a really good example of how that orbital data, and I sort of presented on that early slide, this how we explore planetary surfaces, this kind of linear progression, but of course it's not. We need increasingly sophisticated orbiters to get ground data that helps us then decide and refine where we send landed missions. And in this case, these colors on this are from orbital data telling us there are clays on the surface in this delta region on Mars that would be an environment, the type of environment in which life could originate, hence the choice of that for the Perseverance landing. And of course, here is Perseverance itself being lowered down onto the surface of Mars, having on it a series of experiments, different instrument tools that will help us get closer to this question of did life evolve on Mars? And of course, one of the really fun things about this is an image, I think it's one that just came down, I think yesterday, of the Ingenuity helicopter. So now combining not just mobility on the surface as a rover, but also bringing aerial mobility along. And I have been not joking all along. The Ingenuity helicopter, as most of you know, has a piece of the Wright Flyer fabric on it. And I keep saying that future astronauts have to go pick Ingenuity up and bring it back so that we can put it next to the Wright Flyer in the Air and Space Museum at some point in the future. Sorry, I set an alarm so that I would stop talking. So I think this will be and we're all looking forward to Ingenuity's first flight next week. But this idea of bringing along a recon tool to allow you to better scope out where the rover is going to go next, I think is a really good example of robotic tools. Obviously, the other interesting thing about the Perseverance mission is it's going to lead to that next step of sample return that we've only done on another planetary body at the moon. We've obviously done it for both asteroids and for deep space particles. But we really are looking, and obviously other countries have also done it for comets, but really looking forward to seeing the implementation of the Mars sample return mission that is now notional for the late 2020s. But the problem is, obviously, even with these really wonderful cache samples from Perseverance, they're still going to be really limited. And the problem is, as we all know, is that if life evolved on Mars, which we think there's good scientific reason to think that it would have, what we really want to know is to what degree of complexity did it get? How widespread was it? How varied was it? And one small sample is not going to answer that. And so to me, the only way you're ever going to answer these really complicated questions about the evolution of life on Mars is by sending humans. Because it is this question of not just looking at one rock, but looking at thousands of rocks, not just moving around one crater, but moving around many regions of Mars. And so being able to have humans on the surface is actually the best way to move this forward. But Mars is really hard. Humans are always going to rely on robots in order to be able to function on Mars, whether it's from orbital data, whether it's from reconnaissance tools like small helicopters that can do recon. And in particular, also, I would argue, from things like artificial intelligence that are going to help humans make decisions, especially when they're well out of signal, any kind of immediate signal contrast from Earth. So really important to send humans, but also really important not to underestimate the difficulty in actually getting humans to Mars. But I think just to close, and then I'd love to take questions, when we explore planetary surfaces, our ultimate aim is always to get back to try to understand how planets work, with the ultimate goal of really trying to understand how does the Earth work. And these questions have become even more critical when we look at things like climate change and say we really need to understand how climates evolve and change on other planets. We really want to understand how life evolves and changes and possibly goes extinct on other planets. And I think the Earth is also a really good example of the fact that we best explore and we do the best science when we have humans and robots working together. And it's, to me, always been a false argument of trying to choose between humans and robots. And instead, we should really think about what question are you trying to answer? What is the best tool? And humans are a tool in our toolbox. And how do we move the science forward by choosing the appropriate tool? And how do we keep pushing technology forward as our questions become more and more complex? So thank you, and I will stop there.
So Dr. Stofan, thank you very much for a fascinating talk that laid out both the technological things we got to do as well as the scientific questions. You know, there are some on this Zoom call who are technologists actually studying the advancement of technology. Maybe they'll take some lessons from what you said there. So let's open it up to questions. Can you please, if you have a question, put up your hand, which is in the reactions, and I will call upon you. Questions, anybody? Oh, Jeff Hoffman. So Jeff, do you know anything about Mars?
Well, yeah.
Just a little bit.
Our MOXIE experiment is going to provide some of that show us how to provide that 20 tons of oxygen. But just two comments. The first, related to humans and robots, just to make sure everybody appreciates that right now it takes hundreds of people to operate one little robot on Mars, which really is kind of amazing when you think about it in terms of the relative efficiency of human and robotic exploration. And the second thing that I've always tried to talk to my roboticist friends is, right now we operate Perseverance and all the Mars rovers and everything, so conservatively because there's only one of them. And, unlike the Hubble telescope, we can't go and fix it if it breaks. So we're extremely limited in what we're willing to do. Imagine if you as a roboticist could be on Mars with your robots and able to fix them if they break, and also reconfigure them if their new experiments become available. And so I think that's the real future of human robotic cooperation is having people in the same working area at the same time, in places that humans can get to. Obviously, there's always going to be places that only we can send robots to, but anyway, thanks very much for your talk.
Yeah, and Jeff, those are really good points. And I used to use the example. I think it took the Opportunity rover about 8-9 years to go 26 miles. So I always say, a human, many humans, probably you, not me, can run a marathon in a number of hours. And yet you had this rover that it took 8 years to go that far. And I think human mobility, as you say, risk aversion is a big deal. And it's frustrating to me now with Perseverance. You're like, have we gone anywhere yet? And you're just, not that we wouldn't be very cautious with humans that we send also, but, and I think that human and robots together is really critical. For example, there are zones on Mars that right now the scientific community has said that humans should not go there because there still could be extant life on Mars. There's zones where we think there is water close to the surface. And therefore humans shouldn't go there from both sides contamination. We don't want to contaminate Mars life. We don't want to get COVID, some kind of pandemic disease from Mars life, which I am actually not worried about, but some people obviously are concerned about it. And so the idea that humans could approach zones where we think that water was close to the surface, send robots in to find out if that's true or not, send robots in to actually assess it, see if there is some extant life, is a really critical one. So that humans and robots working together is totally the way we're going to explore Mars in the future. And I think most of us who lived through this versus debate have always been very frustrated. Why are we arguing about this? It's kind of, not a useful argument.
Okay, thank you. So David Newman.
Hi, Ellen. Thank you. That was an incredible talk. Really enjoyed it. I'm looking for students' hands. Oh, good. One's coming up. So I'm going to be quick so we can try to get you more. But trying to channel maybe a question or tee up something for you to comment on behalf of a lot of our students that are watching too. First, thank you for chairing the transition for NASA. That was, I know, an amazing amount of work and effort. So thank you so much for doing that. Maybe what one or two pieces of advice would you give the new NASA leadership team coming on board to help with our lunar? We'll just keep the question to what maybe some words of wisdom for exploring the moon and Mars in the immediate future.
I'm not supposed to talk about anything that happened during the transitions. I have to be, but I have lots of opinions, so I have to be careful how I answer it. So, if you look historically, so this is a whole nother subject, talk to, or hopefully I hope you guys have had one of these talks. If not, you should get one. On this whole issue of the politics, and I think the last, especially 20 years have been super interesting as we've done this moon versus Mars, what became a moon versus Mars kind of discussion. And I think it was particularly interesting, obviously over end of Clinton, I guess through the Bushes, Obama, Trump, now to Biden. of where are we going with human exploration? What is the target? And frankly, when I first got to NASA under Obama, I had someone say to me, oh, the destination actually doesn't matter. And I'm like, no, actually the destination does matter. It matters to me as a scientist, but I think it matters to everyone. You just can't plan human exploration and not care where you're going. And so I do think for NASA, as you look at it being changed from its purpose being changed sort of every 4 to 8 years for human exploration, combined with a lack of resources and very high expectations, makes it very hard for the agency to succeed. And I think the challenge and the opportunity for the incoming administration is going to be the emphasis on balancing presence in low Earth orbit with, again, stop pitting things against each other as we worked on, David. It's not Moon versus Mars, it's Moon to Mars. And so this continuity of purpose that we actually started joking about on the transition team, I think we heard it from every single person we talked to, continuity of purpose. I think that continuity of purpose is really important for NASA, and it doesn't matter what administrations you're talking about, what parties, you've got to let NASA have some continuity of purpose or we're not going anywhere.
Okay, thank you. So George, there's a question from a student.
Thank you, Dan. Thank you, Ellen, very much for your talk. I am a PhD student in the Engineering Systems Lab. I work with Professor DeVeck and also with Professor Hoffman. And I'm kind of following up on Jeff's question about humans and robots on planetary surfaces. So it's interesting that there has been this gap of about 7, 8, and then 10 years between different generations of rovers. Pathfinder in '96, Spirit and Opportunity 2003, Curiosity 2011, and then Perseverance 2021. So the gap is about 7 to 10 years, and it's actually slightly increasing as we're going along. So maybe the other use of humans is not that they're faster scientists and better scientists, but that the cycle of evolution of robots can accelerate when humans are on planets with robots. And I wonder what your thoughts are on that.
You know, I think that's a really good point, because frankly, that 7 to 10 years that you're seeing is actually a pretty typical cycle for NASA flagship missions. You can afford to do a flagship or a multi-billion-dollar mission about once a decade, and that's come out of the decadals. And NASA is often in the Planetary Science Division, and because after the famous ALH 84001, there became a Mars program line in the budget, so there was a little more money. So they could sometimes squeeze 2 flagships in a decade, one Mars and one maybe to the outer solar system. But this is where that funding piece, right, becomes really critical. And then frankly, it's compounded with a risk aversion, right? Because then you're thinking, this is my only chance to go to Mars in this decade. I know it's going to cost me billions of dollars. So do I want to really have a next generation rover? Or am I just going to take more or less a carbon copy of the Curiosity rover because it worked and do it again? So all of a sudden you also get this risk aversion to pushing technology development, because you're, you know, this is my chance to go to Mars in the decade. I'm not taking any risk. And so I really do think that if you saw humans going to Mars, the investment in the robotic technologies would go up, because as you say, humans are going to need these tools to work with. The Human Exploration Program tends to be better funded than the Planetary Exploration Program. And I think there's going to be a demand, right? Because now humans are going to really need these robotic tools. And I think it's going to lead to this much better robots and humans. And for me, that's exciting because that means way more science. And so I think we're going to move into a really exciting point. Whereas right now, we really are limited by this kind of pace of available budget, flagship a decade kind of situation.
All right, it's 3 o'clock, so thank you very much. Let's thank her. Okay.
Thank you. This was really fun. I'm really sorry. I could talk to you guys all day. I'm really
Oh,
sorry. I
that's
have
fine
to
about
run.
it. Thank you, Joyce, for what you did in setting this up. And thank you all for attending our lecture.
Kenya. All right. Thanks, everybody. Sorry, I have to run.
Bye-bye.
Thank you.